Hello, welcome to lecture 14 of Elec Eng2CI5. In this lecture, we'll go over Thevenin Theorem, which is one of the most important theorems we have in electrical engineering. It's used very often in electronics, in analyzing filters, and analyzing power circuits. Very versatile theorem and has many applications. So we'll go over this one. We'll have a number of examples, and we'll see how we can extract the two parameters of the Thevenin equivalent circuit. So we take a look here at a linear circuit. What the theorem is saying is that if you have a linear circuit, and we have here a linear circuit here, and this is one of the ports of the linear circuit. It's simply any two terminals in this linear circuit. So these two terminals are connected to some load resistance RL. Okay, now looking into the circuit, I can replace the whole circuit, regardless of how complicated it is, by what we call a Thevenin equivalent, which is shown here, a voltage source in series with a resistance. Okay, so from the point of view of the load, this whole circuit, which can have current sources, voltage sources, dependent sources, and so on, is actually between these two terminals. It is seen like a 1 voltage source and one resistance. We call this one the Thevenin voltage. We call this one the Thevenin resistance. So our target now is how to extract these Thevenin parameters for any problem. How can we use them? Because once we do that, we can now determine the current going through the resistance RL, because this current will be V Thevenin over R Thevenin plus RL. Okay, so this can be another analysis tool that we can use in addition to loop analysis, nodal analysis, superposition, current division, voltage division, and so on, and all the previous techniques we learned so far. Okay, so the basic idea is between any two terminals of a linear circuit, looking into the circuit, we can replace the circuit by a voltage source in series with a resistance. And now we have to see how we can determine these parameters. And as I said in the previous slide, once you have learned what is R Thevenin, what is V Thevenin, you can now determine the voltage across RL, because the voltage across RL is equal to V Thevenin multiplied RL over RL plus R Thevenin. It is simply a voltage divider, and I can also know what is the value of the current flowing in the load RL. Okay, so this value will be V Thevenin over RL plus R Thevenin. The good thing about this approach is that if you change RL, so if you change RL from 1 kilo ohm to 2 kilo ohm, the Thevenin equivalent is the same. Okay, so you can calculate still the current and the voltage in a very simple way. Before, when we are doing loop analysis and nodal analysis, if you change the value of one resistance, you have to go through all the analysis steps again, because it's a new circuit. Right now, because we replace the circuit between these two nodes, this input port here, by an equivalent circuit. Okay, this equivalent circuit is really independent of the load that you have here. So we can use any load, we can change the value of the load, and we can get our calculations done very fast. So it's a very useful theorem, and it can help us analyze circuits where the load can be changing. Now we move to the second important part. How do we analyze such a circuit? So here we have, this is the Thevenin resistance here. This is R Thevenin. Okay, this is the Thevenin resistance here. I'm still playing with the software. It's new software, and it is the same one here. So now my target is how do we get V Thevenin and R Thevenin? How do we determine these two values? Okay, so the target, what we're going to be doing here, we have to get the value of V Thevenin. What you have to do, you have to simply keep these two terminals open circuit. And this is what you do actually in the lab as well. If you want to determine what is the Thevenin voltage between any two terminals, keep these two terminals open circuit. And if you keep them open circuit, this means in the equivalent Thevenin circuit there is no current flowing. and the voltage you're going to be measuring here, V open circuit, will be equal to V Thevenin. Okay, so this is very important to understand. You replaced your circuit by an equivalent voltage in series with an equivalent resistance. So if you keep this port now, or this between these two terminals, you keep them open circuit, then V open circuit will be equal to V Thevenin because there is no current flowing. Okay, so you have to go to your circuit, and of course RL is not there. RL is the one that's connected between these two terminals, is not there. I don't have it in my circuit. Okay, I'm keeping things open circuit. V open circuit will be equal to V Thevenin. Now, how do I determine R Thevenin? This also you can do in the lab. You create a short circuit between these two terminals. So get rid of RL and create a short circuit. In this equivalent circuit, what you can see, the current flowing will be V Thevenin over R Thevenin. So this I short circuit here is equal to V Thevenin over R Thevenin. So I can simply say, if I already calculated V Thevenin, I can simply say that R Thevenin is the open circuit voltage created by the short circuit current. Okay, so now in order to calculate the Thevenin voltage and the Thevenin resistance between any two terminals, I have to do two simulations or two measurements. The first simulation or the first measurement, create an open circuit, measure the open circuit voltage, and this will give you V Thevenin. Okay, in the actual circuit, you have to keep the terminals open. And if you're doing analysis with a pencil and paper, I will keep these two terminals open circuit, and I will calculate that voltage. The second step, create a short circuit. Of course, in the lab you do the same. You create a short circuit. You measure the current flowing using a multimeter or an ammeter. Okay, current flowing here. This will give you the short circuit current. In circuit analysis, we create another circuit with a short circuit here. We calculate the short circuit current, and then once you have the short circuit current and the open circuit voltage, we have everything, because the open circuit voltage is V Thevenin and the Thevenin resistance is V open circuit over I short circuit, the open circuit voltage divided by the short circuit current. Okay, so it all comes from the equivalent circuit that we are using. It's a voltage in series with the resistance R Thevenin. Okay, there is another approach we can use to calculate the Thevenin parameters. The first one would still require you to create an open circuit at the output port as shown here. So you create an open circuit. So this is the open circuit voltage. And the second one does not require you to create a short circuit here, but it does something very interesting. It takes into account that this equivalent Thevenin voltage represents all the independent sources that you have in your circuit. Remember that this is an equivalent circuit of another circuit which can be large. It can have independent current sources, independent voltage sources, and so on. So this source here represents all the sources that you have in your actual linear circuit. So if we make all voltage sources in the circuit short circuit, so we eliminate them. If we make all the current sources open circuit, then we eliminate them, then this V Thevenin becomes 0. And this is what's happening here. Okay? Then if you connect a source between the input and the output terminals, after you removed all the sources of your linear circuit, then the current that will be drawn from that source will be equal to that external voltage that you collected divided by R Thevenin. So by I extracted here. So I external. So V external over I external will give us R Thevenin. It's a very simple circuit with one resistance. So I can simply say that this is a voltage source. There will be some current drawn from that voltage source. The ratio between the voltage and the current will give you the resistance that you see with R Thevenin. So R Thevenin can be determined by eliminating V Thevenin, by making it equal to 0. How do I eliminate V Thevenin? I go to the original circuit and remove all the independent sources. And here I'm stressing that we handle only independent sources, because dependent sources represent actual components like transistors, like diodes, and so on. So you do not touch dependent sources. You only remove independent sources, independent current sources, and the independent voltage sources. And then when you remove them, you make V Thevenin equal 0. And you should remember, in the same way we did in superposition, when you remove a voltage source, you make it short circuit, because this will give you 0 voltage across it. When you remove a current source, you make it open circuit because you make the current going through it equal to 0. Okay, so this is the second approach here for calculating the Thevenin voltage. Okay, let's take a look at an example. We have a circuit. This circuit has two independent sources, a 36 volt here and 6 ampere. We would like to calculate the current going through the 3 ohm resistor here, and they're asking you for the current if RL is changed to 10. Okay, of course before would use loop analysis, nodal analysis. Nodal analysis here is easier because you have only one node, this only one node, so to have yielded one equation, but you have to do it twice, one for a 3 ohm and one for a 10 ohm. What we're going to be doing here is a little bit different. What we'll do here, we'll simply create a port at this point here and at this point here, and then we try to find the Thevenin equivalent looking into this circuit. So I want to find what's our Thevenin looking to the circuit, looking from the load side to the circuit, and I would like to determine what is V Thevenin as well. Okay, so we'd like to find these two here using Thevenin analysis. So the steps for the solution are similar to what we mentioned before. You create an open circuit between these two terminals, so you get rid of the 3 ohm, create an open circuit, and then you measure the open circuit voltage. You measure it in the lab and you calculate it if you are doing pencil and paper work. Okay, and the second step is we'll create a short circuit here, remove our 3 ohm and create a short circuit and calculate the short circuit current. If I know the open circuit voltage and the short circuit current, then I can determine what is V Thevenin and the R Thevenin for this circuit. Okay, we started now by doing the first part. I removed RL, I created an open circuit here, and I'm now trying to analyze my circuit to determine what is this open circuit voltage. This circuit lends itself more towards nodal analysis because I have only one node here. So I'll take this as my node, and I will take this node here as ground. So I'm gonna call the voltage between this point and ground as 0. Okay, so we create the ground here at the bottom. Okay, this is ground. Okay, so and then we start by analyzing this circuit. So we can simply say that the sum of all currents flowing out from this node will be equal to 0. I have here 3 currents. This current here flowing out is V1 over 6 ohm. This current here flowing out is V1 minus 36 over 12 ohm. And this current flowing out is minus 6 ampere because this is flowing in and then I'm looking for the currents flowing out. So I wrote all these 3 currents here. We sum the terms related to one another, V1 over 6 and V1 over 12. If you take 12 as a common term, you get 3 V1 over 12 will give you V1 over 4. Okay, and then you have here minus 36 divided by 12, so this will give you here so we give you minus 3, you have minus 6, so you get minus 9, you move to the other side, becomes 9. So the equation is now you have V1 over 4 is equal to 9, which is this equation here. Okay, and then which means that the open circuit voltage is equal to 36 volts. So the voltage we will measure between these two terminals, if we keep them open circuit, is equal to 36 volts. Remember, the voltage between here and here is the same as the voltage V1, which is measured between here and ground. Okay, so this is why the open circuit is equal to 36 volts. Now we do the second part, which is to calculate the short circuit current. It is done here in this circuit. So what I did here, I shorted the two terminals of the port I'm looking from into the circuit. Okay, and now I would like to calculate this current. The way we do something like this, you can do it using loop analysis, nodal analysis, whatever. I use superposition here. I found it more easier to use superposition. So I will remove the voltage source, and I will make it short circuit, and I will keep only the current source. So this will yield this circuit for me. From this circuit, you will see that this short circuit that you created is shorting the 6 ohm and the 12 ohm because it's parallel with both of them. So the 6 ampere will flow in the external circuit, and it will completely ignore these two resistances. So the current I1, which is due to the current source only, has a value of 6 ampere. Okay, I'm doing superposition, so I have to do a second simulation in which I remove the current source. So this current source now becomes open circuit, and I keep only the voltage source. So this is how the circuit now looks like. And you want to calculate this current here, this current which is flowing in the short circuit. Okay, you can see that this short circuit again eliminates the 6 ohm from the circuit because it's in parallel with it, and the current flowing will flow in the circuit this way, and the value of this current is 36 divided by 12 will give you here the 3 ampere. It's clear from this calculation it's going to be 3 ampere. So the total short circuit current is the short circuit current due to the current source, which we calculated here to be I1, which is equal to 6 ampere, and the short circuit current due to the voltage source, which we calculated here to be equal to 3 ampere. Then the total short circuit current is equal to I1 plus I2, 6 ampere plus 3 ampere is equal to 9 amperes. So now, as we agreed from our derivation, the Thevenin resistance is the open circuit voltage divided by the short circuit current. So it's equal to 36 divided by the other number, which is 9. This will give you 4 ohm. So we now know the two parameters of the Thevenin model. That V Thevenin is equal to 36 volts. We know that R Thevenin is equal to 4 ohm. We now can go ahead and calculate the currents and the voltages across the 3 ohm resistors that we have, which is our load. Okay, so now this is how the circuit really looks like. At 36 volts in parallel in series with 4 ohm resistor. This is our Thevenin equivalent. So the whole circuit has been replaced between these two terminals by this source and this resistance. And now we connect our load, which is a 3 ohm. Okay, so the current flowing in the 3 ohm resistor from this equivalent circuit, this is an equivalent circuit, it is 36 over 4 plus 3, so it gives us 36 over 7, will give us 5.143 ampere. If you replace this, if you make this one 10 ohm, then the current will be 36 over 4 plus 10. So 36 over 14, and we can do this calculation. It's gonna be 2 point something. Okay. If you make RL equal to 6 ohm, this will be 6 ohm still. So this is gonna be 36 over 4 plus 6. So 36 over 10 will give us 3.6 ampere. So this is the great thing about Thevenin equivalent. It is independent of the load that you connect. It's independent of the load. As long as you found the Thevenin voltage looking into the circuit from between any two terminals, then you can later connect any load to these two terminals and you calculate your currents and voltages and so on. Okay, let's take a look at the second example. We have this circuit here, and they would like us to calculate the current flowing in the 2 ohm resistor. So we'd like to calculate this current here flowing in the 2 ohm resistor. And of course, if they don't show you a direction, you have to assume a certain direction for that current. If you get the current flowing in the same direction, then the value is positive. If you get a current flowing, if you get a negative value, then it means it's flowing in the opposite direction. So I'm gonna assume it's flowing in this direction here, and we'll try to use Thevenin theorem. The way of doing that, well, I have to create a port. So I will create a port at this terminal here and at this terminal here. Okay. So now look. So between these two terminals, I'm gonna remove the 2 ohm. Okay, and then I'll try to look into the circuit from this side. So I'm looking into the circuit from this side. After I remove the 2 ohm, I will replace this complicated circuit with just 1 voltage source and 1 resistor. Okay, this is really my target, and once I do that, I can calculate the current and the voltages in the 2 ohm resistor without any difficulty. Okay, we move now to do the steps. So I redo the circuit again. This is how the circuit looks like. My first step is I'm gonna remove the 2 ohm resistor because this represents a load. I don't need any load here at this point. I will calculate the open circuit voltage between these 2 points, and I will calculate the input resistance. I'm gonna use the second approach, which is calculating the input resistance, and I will explain it to you in a second. Okay, you can of course do the short circuit one. You can make here open circuit, and then you make a short circuit here, and divide the open circuit voltage by the short circuit current to get R Thevenin. This is fine, but I'm going to show you the other alternative approach here. So the first thing is, let's create an open circuit between these two terminals, and let's try to calculate the open circuit voltage. Of course, in the lab, you remove the 2 ohm resistor and then you measure the voltage using a voltmeter. Okay, but using pencil and paper, we create a new circuit where we have open circuit here, and then we calculate this voltage using any of the other techniques we learned earlier: loop analysis, nodal analysis, superposition, whatever the case is, but to get that open circuit voltage. Okay, so I created an open circuit. As you can see here, I have now points A and B, and my target is to find VAB. Find the voltage difference between V and VAB here. So this is open circuit, okay? And the way I decided to do it, I decided to use loop analysis. Well, why did I do that? Because I can see that there is a current source here, there is a current source here, and I can immediately eliminate two equations from these current sources. So just by inspection, I can simply say that I2 is equal to minus 10 ampere, because this 10 ampere and this branch belongs only in the second loop, so I2 is minus 10 ampere. And from this one, this current is flowing in the clockwise direction, while I have 6 ampere flowing in the opposite direction, so I1 is equal to minus 6 ampere. Remember that this current here, this branch here belongs only to loop number 1, in which the current I1 is flowing. Okay, so now I know what's I1, what's I2. I now start to calculate KVL in loop number 3. Let's go around in the clockwise direction. This will give me minus 40. And here I assume the drops happening here in this part to be positive, okay, negative in the direction of the current, and here to be positive, negative. So this is what I do usually when I analyze I use KVL. I assume that the drops are positive and negative in the same direction of the flow of the current of that loop. So I can simply say here, this is the equation. This is minus 40 minus 6 ohm multiplying I3 minus 1 ohm multiplying I3 is equal to 0. There is no drop here because it's a short circuit. So this is the equation. So I can simply write it this way: minus 40 minus 6I3 minus I3 is equal to 0. We collect these two together, this will give us 7. This is minus 40, so I3 is equal to minus 40 over 7 ampere. So I3 has a value 40 over 7, but it's flowing actually opposite to the direction we're assuming. Now, I want to calculate VAB, and I mentioned that in several lectures. If you want to calculate the voltage VAB, you have to find a path that will go from B to A, okay, and then you sum all the voltage drops. Okay, so I choose that path. It's the easiest one because I will have difficulty around current sources, so I go into from here to here. Okay, and I added these drops, and what I'm gonna be showing you here, I'll show you the assumed polarity I have. This is positive, negative, okay, and this one here is positive, negative, and the others are the same. So why did I choose that? I choose them to be positive in the same direction of the current of the loop. So I2 is flowing this way, so I took it positive, negative. I1 is flowing this way, I took it as positive, negative. So this drop will be negative. So I have minus I2 multiplying 3, okay. This one will be negative. I have minus 5 multiplying I1. This one is going to be negative. I have minus 40. This one is going to be negative. I have minus 6 ohm multiplying I3. And I have to include it that way, and then I will substitute for the value of these currents. And these currents are negative, which is fine. So this is what you can see here. This is minus I1 multiplying 3 minus let's go back. This is minus I2 multiplying 3. This is minus I1 multiplying 5. This is minus 40, and this is minus I3 multiplying 6 ohm. And then I substitute with their values. They are all negative. This is fine. Okay? But remember, the reference directions were assumed in this direction, this direction, this direction. All of them in the clockwise direction. If you sum all these, this will give you here 30. This will give you another 30. This will give you minus 40. This will give you here minus 240 over 7. Actually, minus was negative, it becomes positive. So plus 240 over 7. If you sum all this, so these two will give you only 20. So 7 by 20 will give you 120. You add to 240. 7 by 20 will give you 140. You add to 240, you get 380. So this is what we got. This is the open circuit voltage, 380 over 7 volts. Now we move to calculate the Thevenin resistance. One way of doing it is that you create a short circuit, but this is the first approach. Second approach tells you eliminate all the sources and try to calculate the input resistance seen between these two terminals, and this will be Thevenin resistance. So this is what I did here. As you can see, I eliminated the current source that was here, I made it open circuit. I eliminated the current source that was here and made it open circuit. I eliminated the voltage source that was here and I made it short circuit. So now the circuit does not have any independent sources. Okay, so it effectively, this is how the model looks like. And the model now, if you try to see it, this is how it looks like now. Okay, so I have now just R Thevenin, and there is no V Thevenin because V Thevenin now is 0. Because V Thevenin, as we agreed, it represents all your sources. So looking into this circuit here, if you look into this circuit, you must see R Thevenin, and this is what we have here. This is now our circuit after we removed all the independent sources, and I'm warning you again one more time, do not touch any dependent sources. Dependent sources, they do not represent actual sources. They represent circuit components, they represent transistors, they represent op amps, they represent amplifiers. So you should not remove them, they are part of your circuit. Okay, so now if you take a look at this one, what is the input resistance you see? You see that 3 ohm is in series with 5 ohm, and these two are in series with the parallel combination of 1 and 6. So we get 3 plus 5 plus 6 in parallel with 1. 6 multiplying 1 over 6 plus 1 will give you 6 over 7. You add to that 8. This will give you 56 plus 6 will give you 62 over 7 ohm. So this is the Thevenin resistance. Okay, so now we found the Thevenin voltage, we found the Thevenin resistance. We are all set to calculate the current flowing in the 2 ohm resistor. So now we build an equivalent circuit. So what we did now, we replaced the whole circuit between the two terminals connected to the 2 ohm resistor by one resistance, which is Thevenin resistance, and one voltage source, which is the Thevenin voltage source. This V Thevenin represents all your sources, the effect of all your sources. And now we can calculate the current flowing in the 2 ohm resistor. I2 ohm will be V Thevenin over R Thevenin plus 2 ohm. Okay, this is the current flowing in this equivalent circuit. So the whole circuit has been replaced by this one. So you do this calculation, this is 380 over 7, R Thevenin is 62 over 7, and then you add to that 2, this will give you here 14, let's see here, will give you 14 over 7, so this becomes 76, but 76 is double 38, so this becomes 380 over 76 will give you 5 ampere. Of course, the great thing about this approach, if I go now, I change RL to make it 5 ohm, I can do the calculations immediately. I don't have to build another Thevenin equivalent because Thevenin equivalent is independent of the load connected between these two terminals.